Okay. So we'll just pick it up from here. The degree 4 polynomial and behaviors are the same. So on this first one, right end goes up, so does the left end. The next one, right end goes down, so does the left one. And what told us what happened at the right end? What part of the equation? Yes. The sign on the leading coefficient. So the leading term was the term with the largest exponent. The leading coefficient is just the number in front of that term. And so here on, so somebody online, there we go, that has a coefficient of +1, which means my right end behavior goes up. Here I have a coefficient of -2. The negative means my right end goes down. And that's true for any polynomial. So we look at the leading coefficient to determine what's happening on the right end. Then we look at the degree to decide is the other end the same or is it the opposite. So here for this one, my leading coefficient is negative, so right end goes down. The degree is 3, which means the left end will go up. And there we go, we know the end behavior just by looking at that leading term. Yes? Well, we don't have any more information other than that yet. So today we're going to talk about some other features. Some things that we know about the graph would be related to maximum numbers of things. For example, the maximum number of x-intercepts here, well, pretend that's the x-axis. Degree 4 means I can have up to 4 x-intercepts. It doesn't mean I have to have 4, so that here you can see, man, I need to realign, that we only have 2 x-intercepts. So that gives us a maximum. It doesn't tell us how many there actually are. We need more information to know that. Similarly, we can see with these 2 degree 3s, well, yeah, both of these could, well, this one only has 1 x-intercept. This one also just has 1, but it could have up to 3. And turning points, which are the minimums and maximum values, that's 1 less than the degree. So the degree 4 polynomial here has 1, 2, 3 turning points, or there it has just 1. It can have up to 3, but can't have more than 3. And the degree 3 polynomial has 2 turning points. It can have up to 2, it can have fewer, but not more. All right, and that we summarized. That was degree 5. We summarized on this page, and I think this is the page where we left off. So if you weren't here, then you'll need to get this from somebody else, and I'll give you about 20 seconds or 30 as I realign the board here. Any questions with that review? Up to there, we're good? Okay, Karan, Ecom, we doing okay? Okay, so let's move on to this next page. And for question number 1, I'd like you to try it. It's called an example, but I think you could try it. So given what you know about the shape of a graph, here we have a leading coefficient of -3. We know the degree is 4 and the constant term is 2. Oh, we didn't talk about constant terms, but you probably remember. What might this graph look like? There's more than one correct answer, but see what you come up with for this graph. Leading coefficient is -3. Narayan. What does that tell me? This much doesn't tell me that. What you're telling me is true, but if all I know is the leading coefficient is 3, what one thing do I know? So it is talking, is this telling me about the left or right end? Yeah, so the leading coefficient tells me what's happening on the right end. Because when x gets huge, the sign of this coefficient, x is positive, right? So if I'm going to the right, my x is positive, so even if the exponent is like 23, a negative number, I'm still going to have a positive when I get to a billion. To the exponent 23, it's a positive number. But this is the sign that's going to decide, is it going to be continue to be positive or will it be negative? Since this is negative, I know my right end has to have a negative y value. So I know my right end is going to go down like that. But then, what you said, the left end also goes down. What was our clue here? Yeah, degree 4 means the left end is going to do the same thing. So the left end is also going to go down. Okay, then the constant term of 2. Yes. Yeah, I know I have a y-intercept of 2. So do I know anything else? No. I know it can have up to 4x intercepts, but it might not. So probably what I would do is I may even draw these on just to get an idea, but then when it came to actually sketching, to make things line up is always harder for me. So I might just kind of redraw it sort of like that and say, okay, both ends are going down. Then I'll draw this as my y-intercept of 2. And I need to be careful because I'm picky. And one of the things I'm picky with is, did you draw a function? So if you sketch something really quick, sometimes we're careless. There we go. And we draw it so that it gets vertical or it kind of swoops back on itself. So just make sure that it's going to pass the vertical line test everywhere, even though we haven't talked about it a lot. Polynomials are all functions. So anytime you sketch a polynomial, it should pass the vertical line test. I will be watching for it. And if it's close, what I'll do is I'll pick up your piece of paper and I'll hold it on edge and say, there's the x-axis, there's your curve, I think it's coming back. So yes, I will be picky. So, but sometimes people overcorrect and they'll say, well, I'm going to draw it like this. And if you swoop out like that, then I'm thinking, well, wait, a polynomial shouldn't actually swoop out unless it's going to curve up again or kind of curve down again. It has to go to an infinity. So that was a really ugly one. But anyhow, you get the idea. Don't kind of swoop out on the ends here to try to accentuate that it's going to pass the vertical line test. The curve, the concavity actually, the shape of the curve is going to be the same all the way through there. In other words, it's going to be concave down forever, but it's never going to loop back on itself. Yes? Yeah, so the question is kind of what other options do we have here? So I'll sketch a couple of them. You could have kind of one high and one like that. So maybe you don't even have a second maximum. Or it may even just look sort of like that. That's overemphasized. A degree 4 polynomial, and it'll come up more later in this lesson, it can look kind of like a parabola, but it's not a parabola. A parabola has a very specific shape, and there's a relationship that maybe you learned about last year. Did you learn? It would have only shown up in like a 5-minute talk about a focus and a directrix. Sound familiar to anybody? No? Well, let's do a little detour on it's all wacky again. Silly board. Let's try again. New page. There we go. Parabolas. So parabolas can open in any direction. I'm going to have my parabola opening sideways. It's not spectacular. The top half is better than the bottom half. Pretend it's a parabola. Now, it's called a locus definition of a parabola. So locus is talking about location. So where all the points of the parabola show up, remember, just like a line, it's an infinite number of points. So every point on the line has this characteristic. Bad alignment. The characteristic is any point is the same distance from this focal point and from this line. So we'll see if this will work. Okay, so this distance there and this perpendicular distance there have to be the same for it to be a parabola. For a degree 4 polynomial, that's not true. Even if it looks parabolic, it doesn't have this characteristic. Okay, so this is true for every single parabola, that this and that are the same. Or if I came here, this distance, that distance has to be exactly the same, which has some interesting applications. One of which is, you've seen paraboloids all over the place. A paraboloid is a three-dimensional parabola. Where have you seen it? Well, if you've ever used one of those flashlights where you turn the head and then the beam gets focused, it's because the reflector is shaped like a three-dimensional parabola. Or, if you have a satellite dish, it's shaped like a three-dimensional parabola. What's happening with the light is if you need a very special bulb for one of those flashlights, and it's going to have a pinpoint, so it's not going to have a light that's a filament or that's a line. It's going to be just one point that emits light. When you're kind of turning the end of the flashlight, what's happening is this point is moving back and forth in here. And when it reaches the focal point, then as this shines light, the light will come out and it'll go, every beam of light will end up going parallel, like this. The opposite is what a satellite dish does. It's pointed in the direction of a satellite that is not moving, so it turns with the Earth, so it's in the same location always. And then this will receive a signal, and it's just the signal is coming in this way. And what happens is the signal hits the satellite dish and it bounces off, and every signal, no matter where it hits the satellite dish, is gathered at that one focal point. Often the satellite dishes look a little lopsided, so the receiver might kind of be like that. So you have part of the dish and then a bigger part over there. Doesn't matter which part of the parabola you have, it'll always have this characteristic where the beams of information, let's just call them, will reflect to that one point. So that's a characteristic of parabolas. Degree 4 polynomials, nope, they're different. So there are other interesting things that are related to parabolas, but we're going to leave those for today. So here we go. Label coordinates of any points we know. The only point we know for sure is this y-intercept of 2. And other than that, we have a variety of different graphs we could sketch. Questions with number 1. Oh, number 2. Here we have a degree 3 polynomial. We want to sketch the graph. So the instructions at the top here. Sketch the graph of the polynomial without using technology. Okay. Label coordinates of any point you know. So then a hint. You can use the zeros. How do we find the zeros of this? Stod. Yeah, remember what we did in section 2 to factor a polynomial? We can do that same thing here, find all the factors, use the factors to plot x-intercepts, and then use the end behavior constant term to get other features of the graph. So I'm going to give you a couple minutes on this. And do you have a question just for you or for everybody? For this type of question, I wouldn't ask you to put a scale on, but I would expect like if you have a negative 3 and a positive 2, relatively, the 3 is further than the 2. That scale, I'll give you a grid on it. All right, thank you. Let me go over this question. This is actually a polynomial we could factor without using the method we learned with long division and that. We'll talk about that too. But using that process, just a reminder, we look at the factors of negative 4, list them out or store them in your head or something. Remember, we have to look at the positive and negative factors. Even if that constant term was positive, we look at positive and negative factors. And then we start plugging those in to our polynomial. I should have used an f instead of p here. But so f of negative 1 I discovered was equal to 0. And as I mentioned last week, this is a step I want to see. So that first step you can do, show, don't show, that's okay. This step I want you to show me. No, you don't have to show the ones that you tried and didn't work. Just show me one that does work. Okay, so then I know x plus 1 is a factor. So I did synthetic division. You could do long division, that's perfectly fine. So again, the process, these numbers up here are all the coefficients from that polynomial f of x. And out here, this negative 1 is like the negative 1 I plugged into the function. So it's what made this x plus 1 equal to 0. Bring down the 1, negative 1 times 1, and I get negative 1 there, and I add. So for those of you that just joined the class, there's a video that I posted on Edsby that if you message me, I can send you a link tomorrow. Edsby gets updated overnight, so you won't be part of Edsby until tomorrow. But message me or contact a friend, and they could send you the link. Okay, and it'll demonstrate how to do this. So what this tells us is we know x plus 1 is a factor, and here there's the constant, the linear term, the x term, and the x squared term. So I have an x squared minus 4, which I can factor as a difference of squares, which gives me x plus 1 times x plus 2 times x minus 2. And then to find the zeros, I didn't write it on here, but we could just say, well, if I set this equal to 0, what you did with quadratics is still true. If I have 3 things that multiply to give me 0, one of those 3 has to be 0. So if x plus 1 is 0, x is negative 1. That's one of the x-intercepts. If x plus 2 is 0, x equal negative 2 is an x-intercept. And if x minus 2 is equal to 0, then positive 2 is an x-intercept. So that's where I got the x-intercepts up here of negative 2, negative 1, positive 2. Question? As long as you sketch your graph so that the graph goes right to the edges of the grid I give you, I'll assume it continues. If you put a dot at the end, I'll assume you're saying it stops. So if you plot a point right at the end, don't stop your graph there, even go off the edge to show that you want to communicate to me that it's continuing. Good question. Thank you. So then I have a y-intercept of negative 4. How did I find that? Yeah, the constant term in the equation, which we can't see, that negative 4 was my y-intercept. Now, we have limited understanding, as in maybe this was the minimum point. So maybe it dipped down, hit the low point here, and then curved up. I'm not going to be picky about that. I'm pretty sure it didn't, just because the shape of that curve and the shape of this curve will probably be fairly similar, almost rotational symmetry, as if you spun it around, not always. And so if I think of the distance here, because this distance is 3 units, probably the low point is halfway in between. So this is probably not the low point, but if you draw it as a low point, I'm not going to deduct. Okay? Now, any questions before I talk about how we could have factored this one differently? We are good. All right. Suppose you thought back to decomposition. And with decomposition, you would have an x squared term, a constant term, then you take that middle term that has an x, and you'd break it into two terms, giving you four terms. You would group the first two together, and the last two together, keep that negative in there and make this a plus, and then you'd pull out a common factor. So for a degree 3 polynomial that has four terms like this, if it's factorable, sometimes either you can group the first two and the last two terms together, or the first and third and the second and fourth. So it kind of depends. This one, by grouping like this, I can pull out a common factor of x squared from the first two terms, and a negative 4 from the second two terms, and I get this bracketed part that's exactly the same. So there I can see my factor of x plus 1. So why am I showing you this? Bonus information. Because I'm not going to give you a polynomial that's factored like this, at least not intentionally, on a test or quiz, because what I want you to show me is the process we actually showed using synthetic division. But for future reference, sometimes they're factorable. And so we'd pull out that x plus 1, and we'd have the x squared minus 4 left over. All this is equal to f of x. And then that x squared minus 4, difference of squares, we can factor. Mohammed. Yes. Oh, I set it equal to 0 in order to find the x-intercepts. Okay, so that's not the value of the polynomial, but to find the x-intercepts, I make it equal to 0 to give me an equation to solve. Yes? The factoring? Well, when I put the negative there, I changed this to a positive. So it's like I'm adding a negative. But then both of these are negatives. The original question, it's not that I'm distributing this in, because there weren't brackets to begin with. That negative was only with this one term. Good. Yes? Yep. If it wasn't factorable, what I would do is use the quadratic equation to see, is there a 0? And if you find, or just look at the discriminant even. If there are no zeros, so the discriminant is negative, then what you're going to have is, if that's your grid, your graph might look like this. So kind of, you're getting one x-intercept, but you're not getting a second. You're getting imaginary numbers there. And that's from this kind of dip at that part. Is that good enough? Okay. Yes. Ron. Well, in this case, if I had just said, graph this, label the coordinates of any points you know, that should be the flag that, well, I should see if I can find x-intercepts. All right. On to the last big idea for this section. So, one more characteristic for graphs that we're going to talk about is how it crosses the x-axis. And we call that the multiplicity of the zeros. So a 0 is an x-intercept. The 0 of a function is where the function is 0, which means where the y is 0, which means on the x-axis. So we're interested in what happens on the x-axis as the graph goes through. So here we have, before I sketch anything, we'll just compare these three functions. So function is x plus 1, or x plus 1 all squared, or x plus 1 all cubed. So all three of these have a 0 where x is negative 1. But they all touch the graph in different ways. And it has to do with the exponent that they have. So the first one, there we go, has a 0 where x is equal to negative 1. and we'd say the multiplicity of this 0 is 1. That'll make more sense once we do the next two. So whenever I have a 0 with a multiplicity of 1, the graph just does a clean cut through the x-axis. Compared to this next one, I have a 0 at -1, but we'd say it has a multiplicity of 2 because we have this repeated factor. So we could say that g of x is x plus 1 times x plus 1. And if we were looking for zeros, we would set this equal to 0 and solve the equation. We'd get two equations. We'd get this one that says x plus 1 equals 0, and we'd get this one that says x plus 1 equals 0. So, although probably in the past you talked about this point being 1x intercept, and for us all through high school that's good, in the future if you see this, you might be told that there are two x-intercepts, but they are equal. It's kind of like solving this equation. We would say there are two solutions, but they're two equal solutions. So if we think back to the discriminant is that part of the quadratic formula, x is equal to negative b plus or minus square root. The square root part is the discriminant of b squared minus 4ac. So that's the discriminant part, hauled over to a. So there's a song to help you remember it. So if this is positive, we know we have two distinct real roots. If it's negative, we know we have no real roots, which is actually two imaginary roots, which we don't care about now. And if it's equal to 0, there's actually two equal roots. But we haven't been picky about that through high school. And they won't be on the diploma exam. But beyond high school, that may come up. So I thought I'd point it out. So multiplicity of the zeros is 2 whenever I have a factor in a polynomial that's repeated, and it happens 2 times, my graph will bounce off the x-axis like this. This was a quadratic. It would be the same if it was degree 5. But one of the factors would repeat it twice. At that 0, my graph is going to bounce off the x-axis. So, for the next one, this would be a multiplicity of 3 for that 0 of x equaling -1. And what happens with a multiplicity of 3? The factor is repeated 3 times. So that affects how the graph crosses the x-axis. And Miss Pride has called this a hug. So I've adopted that language. So just so you know what we're talking about, we say this, it just kind of comes up, it hugs the line, but then it crosses. So what it's doing is it's going to a horizontal line just for an instant, and then it crosses over to the other side. That's important because I'm picky about that on graphs. And once again, I would pick up your page and I'd follow the curve to see, okay, I'm going to look along the curve, and does it approach the x-axis, or does your curve just kind of go like that? And I would say, nope, not good enough. So be aware. Oh, then the mistake people make is they'll have it come up and then go for a while and then cross over. Also a mistake. So don't do this extreme mistake. Don't do that careless mistake. Just do it perfect. Yay. So what I do when I'm sketching this is actually I'll start from this point and I'll go horizontal and curve away. And then I'll spin my page around to do this part, start horizontal and then curve away. And that just helps me make sure that it's curving to horizontal. Questions? Nope, let's look at a few examples. Well, maybe I'm going to just pause here my talking for a second. As you look at this graph, with your neighbor, what you know about multiplicities and and behavior and kind of everything. What could you say about the polynomial, the equation for this function, whatever it is? So talk to your neighbor a little bit, see what you come up with. How could you describe this? As you see here, I have 6 points that I'm going to come up with. Let me tell you what I came up with, and then we'll see what you have. And I would ask for volunteer information from you, but then I don't know which one of these arrows I should pull out. I suppose I could try. Who could tell me one thing? Wait, Araf. The degree is even. I don't remember which arrow that is. It's not the top 3, and it's not the last one. Nope, I'm not going to pull any of them out. It's not the third one. No, it's not. Oh, so good information. We know the degree is even. Okay, we'll store that in our brain somewhere or on paper. Even degree. Okay. Where's one? Constant term is positive 2. I think that's this one. Yes. The y-intercept is positive 2, which means the constant is positive 2. Moise, thank you. Sorry, what? A negative coefficient of what? Highest degree term. So the leading term is a negative. Ha ha ha! Leading coefficient is negative. Yes, so. Multiplicity of 3. Ooh, which one is that? Is that 1 or is that 3? I think it's this one. Yep. Oh, there we go. 0 at negative x equal negative 2 has a multiplicity of 3, and we know that just from how it crosses the x-axis. Because it curves to horizontal, it hugs it, but then goes across to the other side. Quick comment though, this could be a degree 5 or multiplicity 5. Multiplicity 7, multiplicity 9, we can't tell. It's an odd number. It's not 1 because 1 does a clean cut through. It could be any of the others. For this course, we'll just call that multiplicity 3 for this simplified version. So we'll say that's multiplicity 3. Somebody else. Ethan. It wouldn't be wrong. I would expect to see 3, but it would be correct to say 5 or 7. Well, we wouldn't know. To say it's correct isn't exactly right, but we can't tell. It's possible. Put it that way. Econ. The multiplicity, well, we just know that that's the multiplicity here. Each of the other x-intercepts can have different multiplicities. I'm looking for new hands. Not those same old hands. Alicia. Excellent. Yep. Yeah. So tell me about this one. What's the multiplicity? Yep, there we go. So we have a 0 at x equal 1 with a multiplicity of 2. So at least a degree of 6. Did I put that here? Yeah, so that's where I put the even degree. Has to be at least degree 6. Would be better if we talked about this other multiplicity first. We have a 0 at x equal 3 with a multiplicity 1. So because we have a multiplicity 1, 2, and 3, add those up, you get 6. It has to be at least 6. We know it's even, so it could be 8. We can't tell, but it has to be at least 6. Yes? Yep, could be a 6 or any even number higher. Okay. Who needs a minute to talk to their neighbor to clarify something here? Okay, 1 minute. Talk to your neighbor. Our next question. We want to write an equation in factored form for the polynomial. So what we know is, well, we'll scroll so we can see that much. I have a 0 at x equal negative 2 with multiplicity 3. So what's the factor that corresponds to x equaling negative 2? X plus 2. So I know I have an x plus 2 with an exponent of 3. Man, my alignment went off again. Must be the heat. And for the next one, I'll have an x minus 1 with an exponent of 2 because of that multiplicity of 2. And then I'll have an x minus 3 with an exponent of 1. But just like with quadratics, there could be a coefficient multiplied out in front. And so I'm going to assume that there is, and in fact, I know there has to be, because my right-hand behavior is negative. If I was to expand this out, this I'd get an x cubed, I'd get an x squared, I'd get an x, they'd all be positive. I need a negative leading coefficient. So this a is going to have to be negative. But it might not be a negative 1. So did I have, nope, no letters up there. Let's just call this y equals that. Can you figure out what that a value is? I think you can. Oh, yes. Oh, it's not that bad. Well, even just the y-intercept. You know the y-intercept, you know the ordered pair, plug in the x and the y. There you go, solve for a. So I'll give you a minute to do that. Well, we can't see it until we expand it out. So there we go. I know the y-intercept is 0, x is 0, y is negative 2. So we'll make the y 2. All the x is 0. So then I'm just going to do 2 cubed is 8. Negative 1 squared is 1. Negative 3 times 8 is negative 24. That's where this negative 24 came from. All of that times a equals 2. And I solve for a to get negative 1/12. So you could plug this into your calculator, and you should see a graph that looks like this. Depending on the scale, it might look a little bit different, but basically this is what you should get when you plug it in your calculator. So I'm going to give you time to plug that equation in to compare with your graph. Yes, Jasmine. Where does the constant term go? So imagine that this is, well, imagine this is the equation. And if we think of the y-intercept, when it's in factored term, we can't see the constant. So we'd plug in a 0, we'd get the 8. Plug in the 0, get a 1. Plug in the 0, get a negative 3. So I'd have negative 1/12 times negative 24. Then I would get a positive 2. So I'd actually have to do some work to find that constant term. Yes? Why did I do what? Oh, this is a 3. It's just a little bit messy. Exactly. Math. It's amazing. It's like magic. Once you've checked that out, the next 2 questions are check your understanding, see what you can come up with for sketching those 2 graphs.